On March 11, 2019, a pulsar in the globular cluster Terzan 5 did something that should have been impossible. It stopped ticking. Not forever, not completely, but for 38 minutes, an eternity in the life of a pulsar. Its signal flatlined. The radio telescopes heard nothing. No pulse, no rhythm. Just silence where there should have been the universe's most reliable clock. Pulsars do not stop. They are the remnants of collapsed stars, spinning hundreds of times per second, broadcasting their rotation like cosmic lighthouses. They are so precise that astronomers use them to detect gravitational waves, to navigate spacecraft, to test the limits of Einstein's relativity. They do not pause. And yet, PSR J1748-2446 AD paused. I found the anomaly buried in an observational report, a footnote really, marked for further study. But as I traced the data backward, I realized this was not the first time. Other pulsars had frozen, other clocks had stopped, and each time, the explanations grew stranger, the implications deeper. This is a story about what happens when time itself becomes negotiable. Pulsars were discovered by accident. In 1967, Jocelyn Bell Burnell, a graduate student at Cambridge, noticed a strange blip in her radio telescope data, a signal repeating every 1.337 seconds. So regular, so precise, that her supervisor, Anthony Hewish, half-joked it might be aliens. They called it LGM-1, Little Green Men. But within months, Bell Burnell found 3 more. Same pattern. Different stars. Not aliens, something stranger. The signals were coming from neutron stars, objects so dense that a teaspoon of their material would weigh 1 billion tons. When massive stars collapse, their cores compress into spheres just 20 kilometers wide, spinning at incomprehensible speeds. As they spin, they emit beams of radiation from their magnetic poles. If Earth happens to lie in the path of that beam, we see a pulse, a cosmic lighthouse, flashing in perfect rhythm. I spent weeks reading through the early pulsar catalogs. Hundreds of them now, scattered across the galaxy. Some pulse once per second. Others, millisecond pulsars, spin 700 times per second, faster than a kitchen blender, packed into a sphere the size of Manhattan, and their timing is extraordinary. The best pulsars, millisecond pulsars like PSR B1937+21, are more stable than atomic clocks. Over decades, their pulses drift by less than a microsecond. Astronomers use them to create pulsar timing arrays, networks of cosmic clocks that can detect ripples in spacetime itself. They are the universe's metronomes, constant, unchanging, eternal. Or so we thought. By the early 2000s, astronomers began noticing glitches. Brief moments when a pulsar's spin rate would suddenly change. A hiccup in the rotation caused by starquakes deep in the neutron star's crust. These glitches were rare, violent, and short-lived. Within days, the pulsar would settle back into its rhythm. But glitches are not pauses. They are accelerations, not silences. What happened to PSR J1748-2446 AD in 2019 was different. Terzan 5 is a globular cluster, a dense sphere of ancient stars in the constellation Sagittarius. It lies 19,000 light-years from Earth, near the galactic center, where gravity is strong and space is crowded. Within Terzan 5, there are at least 33 known pulsars. It is one of the most pulsar-rich environments in the galaxy, and among those pulsars is PSR J1748-2446 AD, the fastest spinning pulsar ever discovered. It rotates 716 times per second. Its equator moves at nearly 1/4 the speed of light. If it spun any faster, centrifugal force would tear it apart. It sits at the edge of physical possibility. A star spinning so fast that time itself should be dragging in its wake. In March 2019, the European Pulsar Timing Array was conducting routine observations. They were monitoring dozens of pulsars, looking for patterns, gravitational waves perhaps, or subtle shifts in rotation caused by the interstellar medium. And then PSR J1748-2446 AD went silent. The first pulse arrived at 0317 UTC, as expected. The second pulse, 1.4 milliseconds later, the third, the fourth, and then nothing. For 38 minutes, the telescopes heard only noise, No pulse, no pattern. Just the hiss of the cosmic background, punctuated by static. At 0355 UTC, the pulsar resumed. The same period, the same phase, as if nothing had happened. I kept returning to the observation logs. The data was clean. No instrumental failure, no interference. The signal had simply stopped, and then, without explanation, started again. A brief alert was circulated to observers, the kind that lives in astronomers' telegrams and internal logs. Anomalous pulse dropout observed. Cause unknown. Further observations required. But I found something else in the archive. A reference, buried in an early 2000s report, to a similar event. PSR J1748, one of the most stable pulsars ever discovered, had also gone silent for 9 minutes in 1998, and there were others. I began pulling files on every reported pulsar anomaly from the past 30 years. Most were glitches, sudden spin-ups, caused by cracks in the neutron star's crust. But scattered among them were events like Turzan 5, moments when the pulse simply vanished, as if the star had been erased from time. PSR B 1937+21, 9 minutes of silence, October 1998. PSR J1748-2446, AD, 38 minutes, March 2019. 2 confirmed events in the record I could trace cleanly. 2 different pulsars. No common environment, no shared characteristics. One in a binary system, 2 stars orbiting each other. Another isolated. One near the galactic center, another in the disk. But here was the pattern. It wasn't the duration that mattered. It was the silence itself, perfectly clean, as if each star had taken a synchronized breath across decades. But they all shared one feature: extreme density. Neutron stars are already among the densest objects in the universe. But millisecond pulsars, spun up by accreting matter from companion stars, push even closer to the limit. At their cores, matter exists in states we cannot replicate in laboratories. Quarks might dissolve into strange matter. Neutrons might collapse into something denser still. And at those densities, Einstein's equations begin to behave strangely. General relativity predicts that gravity warps spacetime, bends it like a heavy ball pressing into a rubber sheet. Near a neutron star, time moves slower than it does far away. This is gravitational time dilation, confirmed by countless experiments. But most models assume smooth, stable conditions. What if conditions inside a pulsar are not smooth? Imagine standing beside a clock that suddenly freezes while your heart still beats, your breath still moves, but the second hand refuses to tick forward. For the pulsar, that moment stretched for 38 minutes. For us, it was a message from the edge of time. In 2016, a team at the Max Planck Institute for Gravitational Physics ran simulations of neutron star interiors. They modeled what happens when the core undergoes a phase transition, when the matter inside reorganizes into a denser state. The simulations showed something unexpected: localized pockets of extreme curvature, moments when spacetime inside the star warps so violently that time, from an outside perspective, appears to stop. Spacetime twisted like glass under pressure. Not truly stop, but slow to a crawl. Stretched so severely that seconds inside the star become minutes outside. If a pulsar's magnetic poles pass through such a region, even briefly, the beam of radiation would fail to reach us. The pulse would vanish, not because the star stopped spinning, but because its clock had become disconnected from ours. The silence wasn't emptiness. It was the sound of reality holding its breath. I found myself circling a question. If time can stop inside a star, what else have we missed? Time dilation is not new. We have known since 1915 that gravity slows time. Clocks on GPS satellites tick faster than clocks on Earth's surface because they orbit in weaker gravity. Astronauts on the International Space Station age slightly slower than people on the ground. These effects are tiny milliseconds over a lifetime. But they are real, measurable, predicted by general relativity. But those are weak field effects, gentle distortions, in calm spacetime. Neutron stars exist in the strong field regime, where spacetime curves so sharply that the equations become unstable. At the surface of a neutron star, gravity is 2 billion times stronger than on Earth. Time runs on the order of tens of % slower than it does in empty space. And at the core, we do not know. The mathematics of general relativity break down at certain densities. Einstein's equations yield infinities. Singularities. Places where the laws of physics, as we understand them, cease to function. Black holes sit beyond that threshold. Neutron stars, we believe, sit just shy of it. But what if some neutron stars cross the line? In 2018, a paper from the Perimeter Institute explored a radical idea: transient singularities. Not permanent black holes, but brief moments when space-time inside a neutron star curves so steeply that it mimics a black hole's behavior, trapping light, freezing time, distorting causality. The mathematics were speculative, the physics barely testable, but the idea fit the data. If a pulsar's core underwent a sudden compression, perhaps during a starquake or a phase transition, it could create a pocket of near-infinite curvature, a temporary trap where space-time bent so sharply that light couldn't climb out. For a few seconds, by the star's own clock, the interior would behave like a black hole. Radiation could not escape. Pulses could not form. If clocks could dream, this is what it would look like. And from Earth, watching through telescopes, the pulsar would simply vanish. I kept thinking about the implications. If time can stop inside a star, does the star experience it? Does the matter at the core know it has been frozen? Or does time, from its perspective, flow normally, while the rest of the universe races ahead? These were not idle questions. They touched something fundamental about the nature of time itself. We think of time as absolute, a universal river flowing forward at the same rate for everyone everywhere. But Einstein proved otherwise. Time is local. It bends with gravity, stretches with velocity. Two observers, moving differently or sitting in different gravitational fields, will measure time passing at different rates, and both will be correct. This is not an illusion. It is the structure of reality. But we still rely on clocks, on the assumption that most of the time, most places, time flows consistently. We synchronize satellites, calibrate telescopes, schedule observations, all on the belief that the universe ticks forward in an orderly fashion. Pulsars were supposed to be the ultimate clocks, unchanging, reliable, immune to the chaos of the cosmos. But PSR J1748-2446 AD showed us something else. It showed us that even the most stable clocks can stop. That time, at the extremes, is not just flexible, it is fragile. I began thinking about other places where time might break. Near black holes, famously. An object falling toward the event horizon would appear, to a distant observer, to slow down, redden, and freeze, never quite crossing the threshold, suspended forever at the edge. But black holes are permanent. Their time dilation is eternal. Pulsars, it seemed, could do something stranger. They could pause time and then release it. In 2020, a team at Caltech proposed a new model. They suggested that millisecond pulsars, spinning so fast, packed so tight, might generate transient erga regions, zones where spacetime is dragged along by the star's rotation. Inside these regions, time and space become tangled. Light can no longer travel in straight lines, and the pulsar's beam, instead of shooting outward, could spiral inward, trapped. For minutes, maybe longer. The model was theoretical, untested, but it explained the silence. If light can be trapped by rotation alone, what else can a spinning star steal from time? What else can it take? And it implied something more, that pulsars, the universe's most reliable clocks, might actually be teaching us that time is not reliable at all. I will admit, there was a moment, reading through these papers, when I felt something close to fear. Not fear of the stars, not fear of the physics, fear of the implication. If time can stop for a pulsar, if it can stutter, freeze, restart, then time is not the foundation we thought it was. It is not the stage on which the universe performs. It is part of the performance. Mutable, breakable, dependent on conditions we barely understand. We build our lives around time. We measure it, plan by it, trust it to be constant. We assume that a second today is the same as a second yesterday, that clocks in different places tick at comparable rates. If your wristwatch froze, you'd tap the glass. The universe does not tap. It waits, but near a neutron star, a second stretches into minutes. Near a black hole, it stretches into eternity. And if our most stable cosmic clocks can pause, what does that say about the nature of now. But fear gave way to fascination. Because what these pulsars revealed was not chaos, it was depth, a richness to the fabric of space-time that we are only beginning to map. Time is not a rigid grid. It is a field, like gravity, like electromagnetism. It can be warped, compressed, dilated. And at the extremes, inside neutron stars, near black holes, perhaps in the early universe, it can behave in ways we have never observed, never predicted, never imagined. The silence of PSR J1748-2446 AD was not a failure. It was a message, a reminder that the universe is stranger than we know, that even our most precise instruments, our most elegant theories, are approximations maps of a territory far vaster and weirder than we can yet comprehend. I return to the data one last time. In 2023, astronomers observed PSR J1748-2446 AD again. For 18 months, they monitored it continuously. No dropouts. No anomalies. The pulsar ticked on, 716 times per second, as steady as ever. Whatever caused the silence in 2019, it did not repeat. Or perhaps it did, and we were not watching. We will never know, with certainty, what happened inside that star. We cannot see through the neutron degenerate matter, cannot probe the core where space-time twists into knots. We can only measure the echoes, the light that reaches us, the pulses that do or do not arrive. But the lesson is clear. Time is not universal. It is not absolute. It is a feature of the universe that depends on mass, motion, and curvature. And in the most extreme environments, it becomes something almost unrecognizable. A pulsar silence is not an error. It is a glimpse into the deep structure of reality, a place where time itself is negotiable. We have built our physics on the assumption that time flows, that it ticks forward, 1 second at a time, the same for everyone. But the universe does not care about our assumptions. It is under no obligation to be simple or intuitive or kind. It simply is. And in that silence, in those 38 minutes, when a star's clock stopped, we heard something profound. Not the end of time, not the failure of physics, but the realization that time, like light, like space, is something far stranger and more fragile than we ever dared to believe. I closed the file on PSR J1748-2446 AD, but I left it marked for further study because the mystery is not solved. It is only better framed. Perhaps the silence was a phase transition. Perhaps it was a pocket of curved spacetime. Perhaps it was a quirk of the interstellar medium, a fluke of observation, a ghost in the machine. Or perhaps it was the universe reminding us that time, the one thing we thought we could count on, is just another variable, another field to be warped, another clock to be stopped. 38 minutes of silence, enough time for light to travel from the sun to near Jupiter's orbit, enough time for us to realize that even the universe can hesitate. And perhaps that is the beauty of the archive, that even time itself is subject to revision. Somewhere, 19,000 light-years away, PSR J1748-2446 AD keeps spinning, a tiny ember in the dark, a heartbeat in the silence, reminding us that even time forgets to move, and so the archive grows. Another theory shelved, another mystery opened. The clock resumes. For now,